Okay, well, let's get going here. Just checking to make sure I had the voice working, which I think I do. So we're going to start on Chapter 5's problems now. The first couple are pretty easy. And I was just having a little problem there with my ear liner. Okay, so we're going to do problem number 6 here. It's on page 153. It says a horizontal force of 150 newtons is used to push a 40-kilogram packing crate a distance of 6 meters on a rough horizontal surface. If the crate moves at constant speed, find the work done by the 150 newton force and the coefficient of kinetic friction between the crate and the surface. So let's draw ourselves a picture. So here's our crate. And here's our surface. We're going to have a force acting like this, and we're also going to have a counterbalancing friction force. So this is the force, and we'll call this small f. Okay, so the horizontal force is equal to 150 newtons. And since it's traveling at constant speed, F also has to equal 150 newtons. And, okay, so we push it 40 kilograms, so it has a mass. Mass equals 40 kilograms. And we push it a distance of 6 meters, so delta x equals 6.0 meters. Let's define a coordinate system, so this is positive x. Okay, so let's find the work done by the 150 Newton force. So work is equal to force. When you have a constant force, it's just equal to the force times the distance. And this force is pushing in the positive direction. So the work done by the 150 Newton force is positive. So you have 150 newtons times delta x, which is 6 meters. And you multiply this together and you get 900 Newton meters. Now, a Newton meter is a joule, so we can just rewrite that in another. It's not a base unit, but it's a derived unit. Okay, the coefficient of kinetic friction between the crate and the surface. So let's put these on 2 pages. So the coefficient of friction, kinetic or static friction, is the ratio of the friction force to the normal force. And so if we draw a free-body diagram of this block, or whatever we call it, packing crate, what we have pushing up on the crate is we have the normal force, and pulling down is the weight. So this is equal to the weight, and the weight is just always mass times g. So that's that, and then we have the normal force here. And if you sum the forces in the y direction, in this case, it's equal to 0 because there's no relative movement up or down. It's all parallel to the surface. So what we have is we have pushing, and let's define positive y. It's going up, so we have n going up. We have weight going down. Therefore, the normal force is equal to the weight. If you solve that, and the weight is the mass, which is 40 kilograms times the acceleration due to gravity, which is 9.8 meters per second squared. So we'll multiply these 2 terms together. 40 times 9.8 is 392. And the answer in newtons, kilogram meters per second squared, which is a newton. So let's put 392 newtons. So that's that part. We know the friction force has to equal the pushing force because otherwise we'd accelerate. And it specifically says in the problem that it does not. It says it goes at constant, that's the exact words they use, constant speed. So we have 150 newtons of friction. We have 392 newtons of a normal force. So the ratio of those two is the coefficient of friction. It's called the coefficient of kinetic friction because things are moving. So let's just do it to 2 decimal points. So it's a dimensionless number because we divide newtons by newtons. So this is another example of a dimensionless number. We have things like degrees, radians. Those are dimensionless numbers as well. Okay, so I'm just going to pause and make sure I didn't make any mistakes. Hopefully not. Okay, so this is the correct answers. The only thing I would add to this is just a comment here. The force is actually, the work is actually force times displacement times the cosine of the angle theta. And that's the angle between the force and the movement. In this case, the angle is 0. So we have a specific case of theta equals 0 degrees. So when you do this, you get the cosine of 0, which is 1, and you simplify that to the. Now, if I had been pushing the force at an angle, say in this direction, some angle, it would be only the force, component of force, and the direction of the movement. So we could take a force. Let me add a page so I can kind of explain what's going on here. So if we drew this block in this direction, and then we apply the force like this, and let's assume that it makes a 30-degree angle with respect to the horizontal. So this is 30 degrees. And we displace this thing as the same amount, 6 meters. Let's say the force is still 150 newtons, but it's not directed along the movement, but is at an angle. So in that case, the work would be equal to the force, 150 newtons, times the displacement along this surface, x, which would be 6 meters, times, and we use the cosine because that's basically what we're doing is we're going to break this up into a y component and an x component. So this cosine of 30 times that gives us the x component of force. So you're taking the component of the force in that direction, or you're just using this equation more blindly. And so in that case, the amount of work done would be less. The friction force would have to be also less, or the coefficient of friction would have to be less for that thing to move. That may not be obvious at this point, but I'm not going to go into it. So in this case, we have 780 joules. Be Newton meters, which we can convert a Newton meter to a joule. Okay, so that's all I have to say about that. Our next problem in the assignment is problem number 8. This has a blue, so it's a little bit harder. So let's read the problem first. A block of mass 2.5 kilograms is pushed 2.2 meters along a frictionless horizontal table by a constant 16 Newton force directed 25 degrees below the horizontal. Determine the work done by the applied force, the normal force exerted by the table, the force of gravity, and the net force on the block. So let us draw a picture. So here's our block again. Here's our frictionless surface. Frictionless means there's no friction force. Okay, so there's a block. It has a mass. Let's write it down. Mass equals 2.50 kilograms. And it's pushed in the x direction, let's just use the middle of the block as a reference point. That's x. And it goes along the distance, so that delta x is 2.2 meters. Okay. As pushed by a 16 Newton force directed 25 degrees below the horizontal. So I think how I'm interpreting that is, I think I was pushing it downward. So if we push like that, and then we draw a horizontal line here, so that's just a reference line. This angle theta is equal to 25 degrees, 25.0 degrees. So one way you can look at this is you have this force, and it can be broken up to an x component, a y component and an x component. And before we start, this force was equal to 16.0 newtons. Notice I have three significant figures going through here. So, and this angle is 25 degrees, so this angle is also 25 degrees. So you could say this is f sub x, that's the x component, this is f sub y. And to find the work, all we have to do is just, the distance is in this direction, x. So we'd use the f sub x form of the force. So what's the first question? Determine the work done by the applied force. So the work is, you could say F times delta x times cosine of theta, or you could just say it's F sub x times delta x. So let's just plug the numbers in here. So we have the force, which is 16 newtons, times delta x, which is 2.20 meters, times the cosine of the angle theta, which is 25 degrees. So let's see what we got. 16 times 2.2 times cosine, let me make sure I got it in the right node, it's in degrees, 25 cosine 25. And I get 31.9. Okay, work is Newton meters. It's also joules, 31.9 joules. Okay, so that's part A. Part B says the normal force exerted by the table. So let's draw another picture, which is the same block, but we're going to show the forces acting on this. And we're actually going to, because we're not rotating, they all kind of meet in one place. So, well, let's do it this way first. So we have this force pushing down, which has the x component and the y component. We're dealing with the normal stuff. We're dealing with the y component. We dealt with the work. We dealt with the x component. So this is F sub y. Pushing upward is the normal force. That's the force normal to the surface. We'll call that N. It's frictionless, so we don't have any. All it's going to do is cause it to accelerate. And then we also have the weight. So we have the weight of the object force due to gravity that's pushing downward. Let's put it about right there. So that's our weight. That's equal to the mass of the object times the acceleration due to gravity. So did they give us the mass? Yes. Okay, so the mass, we already wrote that down previously, 2.50 kilograms. And so if we were to sum the forces in the y direction, for one thing, we would get 0 because there's no movement in the y direction. All the movement is in the x direction. And what do we have? We have, pushing down, we have f sub y, so we put a negative sign. We have the weight, which is pushing down also, so it's going to be minus w. And pushing upward is a normal force. So those are the three forces. So the weight pushes it down, and also because this force has a downward component, that also adds. So when we finally solve for n, the normal force, it's just f sub y plus f sub w F is the weight, F sub y is F times the sine of the angle theta. So if we want to plug the numbers in, we have the force, which is 16 newtons times the sine of 25 degrees, plus the weight, and the weight is the mass times the acceleration due to gravity. So the mass is 2.5 kilograms times the acceleration due to gravity, which is positive 9.8 meters per second squared. So 16 times the sine of 25 plus 2.5 times 9.8 is 31.3 newtons. Is that right? Yeah, it's force, so it's newtons. So that's the normal force. That's holding up the weight as well as some of this force that's pushing on it. Force of gravity. Well, force due to gravity is just the weight, so part C is just weight. And so that's 2.50 kilograms times 9.8 meters per second squared. So you multiply 9.8 times 2.5 and you get 24.5 newtons. So that's the force of gravity. And the net force on the block. Well, there's no net force in the vertical direction because there's no movement. So the only net force is in the x direction. And so the net force is really just F sub x. Because it says frictionless, I think. So F sub x. And we calculated that over here. Well, actually, we didn't. It's just going to be 16 newtons times the cosine of 25 degrees. So 16 times the cosine of 25 degrees is 14.5 newtons. We assumed that it was moving to the right, and because this answer is positive, that's true. And that net force is going to cause this thing to accelerate. We could calculate the acceleration, have an acids for it. We could just take the force divided by mass, and that would calculate the acceleration. So those are my answers, so let me see if they're right. Okay, so I made a mistake in that I read the problem wrong. Nothing I've said is wrong, but I just didn't answer the question. So the first part was, what is the work due to the applied force, which is 31.9. The second part of the problem asks, what is the work done due to the normal force? Well, the normal force is perpendicular to the movement, so the work done due to the normal, so we want to do work done due to the normal force is 0. So you always have to be in the direction. So this one's 0. The work due to the weight is also 0. It seems counterintuitive, but since we are moving in this direction and the weight is pointing downwards, we have an angle of 90 degrees, and therefore the work due to gravity is also 0 joules. And so the net due to these forces is the sum of the three, and so if we take the net force times the distance, which is what we have here, we would get that the total work is just equal to the sum of, you could just add these three together, so it's 31.9 joules plus 0 joules plus 0 joules, and so the answers for part A and part B are the same thing. So that's correct. So it shows you got to read the question. Okay, so we're on problem number 13, chapter 5. So let's read it. It says a 70-kilogram base runner begins to slide into second base when he is moving at a speed of 4 meters per second. The coefficient of friction between his clothes and the earth is 0.7. He slides so that his speed is just 0 as he reaches the base. How much mechanical energy is lost due to friction acting on the runner? How far does he slide? So in this chapter we're dealing with work and energy. And so we have basically the change in energy. And in this case, so we have the base runner. So here he is. And he slides on the ground. Actually, it should be going the other way, but this is how he's looking. We're looking from the outfield. And so we have the mass is 70 kilograms. We have has an initial velocity. We'll call that v sub I. So v0. We tend to use f and final and initial when we're dealing with energy problems. Don't know why, but we do. Coefficient of friction is 0.70. So that's the ratio of the friction force to the normal force. And the normal force in this case is just equal to the weight, because you have the weight pushing down and the normal force pushing up. Okay, so that's the normal force, and it's just actually that's the weight, which is equal to the mass times acceleration due to gravity. So the idea is that there's really two things happening. There's a decrease in energy because of the going from 4 meters per second to 0 meters per second. And since these are the same height, there's no change in potential energy, so it's just change in kinetic energy. So what we can say is the energy lost is just the decrease in kinetic energy. So we take 1/2 mv final square, that's final kinetic energy minus initial kinetic energy, and that's the amount that he's lost. That's the change in kinetic energy, which is the amount lost. So we just have to take 1/2 times 70 kilograms times the final velocity, which is, you could factor out the 1/2 of the mass, so you'd have 1/2 m times the difference of those velocities. So you get 0 meters per second quantity squared minus 4.0 meters per second squared. And I got to get my calculator. Okay, so we're going to have 0.5 times 70 times 4 squared, which is 16. So we get 560 kilograms meters squared per second squared. And a kilogram meter per second squared is a newton. So that's 560 newton meters. And a newton meter is a joule, so we have 560, and it's actually negative, but they asked for how much is lost, so it's really, I guess, positive, if you want to be exactly correct. Okay, so that's the energy loss. Then it says, how far does he slide? Well, there's a couple of ways you could do this. You could do it by calculating his deceleration. So let's look at the two ways you could do it. One using energy considerations, one using conservation of energy. So, using kinematics. So the kinematics part is if we know 3 out of the 5 things that we usually are interested in, then we're okay. So what do we know? We know V0 is 4 meters per second. We know that V is equal to 0 meters per second. And what else do we know? Do we know anything else? Actually, I'm not sure if we can solve it that way. We'd actually have to use Newton's second law. Okay, so we can't. We don't have enough to solve it that way. So you could do the sum of the forces in the x direction. We need an acceleration, so we could sum the forces in the x direction. And what you'd have is you'd have the friction force, which would be pointing in the negative x direction, so it would be negative, and that would be it, and that would be equal to mass times acceleration in the x direction. And the friction force would just be equal to the coefficient of friction times the normal force, and that's mu times the normal force is the weight. So you get mu times m times g. So we plug that in there, you would get minus mu m g is equal to m times a sub x. Mass cancel out. And so a sub x is just equal to negative mu times the acceleration due to gravity. And mu is 0.7, g is 9.8 meters per second squared, and you have 9.8 times negative 0.7, and so his acceleration, which would be negative 6.9 meters per second squared. And you can use that acceleration and two velocities to calculate distance and time. We'll go ahead and complete the whole thing. Why not? Hopefully I've done this right. I think I have. If it doesn't, then we'll go back and figure it out. Okay, so if this is acceleration, you have v is equal to 4 meters per second, and you have v0, and you have that is 0 meters per second, and you want to calculate, what do we want to calculate? Delta x. So you remember v squared is equal to v0 squared plus 2a delta x. This is 0, so you get v0 squared is equal to negative 2a delta x. You can solve for delta x, so delta x is equal to negative v0 squared over 2a. So you get negative v0, which is 4.0 meters per second. Square that, divide by 2 times acceleration, which is negative 6.9 meters per second squared. So we get delta x is 16, which is 4 squared, divided by 2, divided by 6.9. The negatives cancel out, and you get delta x is 1.16 meters, which is a little over 3 feet. Okay, so that'd be one way of doing it. That's Chapter 4 way of doing it. Now, Chapter 5 way of doing it is you have that the work is equal to the change in kinetic energy and also potential energy, but there's no potential energy change because it's all at one height. The work is equal to the force times the distance. And let me make sure I got the sign right here. So I have, well, the work, you've got to figure this out. So delta x is this direction. The force is that direction because it's slowing us down. So this is going to be a negative quantity. So we just have to make sure we can take that into account. So this is negative, and F is equal to mu times the normal force, just like before. This is the friction force. So that's mu times the mass times acceleration due to gravity. So, so this is going to be equal to, the work is going to be equal to the change in kinetic energy, which is 1/2 m times v final squared minus v initial squared. And so if we solve for delta x, it's going to be 1/2 m v final squared minus v initial squared divided by the force. But the force is going to be a negative number because it's opposing the direction of motion. So we have a negative sign right there. So if we plug in, we get 1/2 times 70 kilograms times v final squared, which is 0 meters per second squared, minus V initial, which is 4.0 meters per second squared, divided by minus mu, which is 0.7, negative mu, mass, which is 70 kilograms, times G, which is 9.8 meters per second squared. And if we look at what we have here, we cancel the mass out. And so then all we have is 0.5, which is a half, divided by 0.7, divided by 9.8, times 4 squared, which is 16. And the negatives cancel out because we've got a negative here, a negative there. So we get a positive delta x, and we get 1.17. I think it's just because of rounding off, 1.17 meters. That compares with 1.16 meters we got the other way. So those are the two ways. You can use Newton's second law to calculate the acceleration. Once you have the acceleration, you can then use constant acceleration equations to calculate the delta x. You can also calculate the time. And up here, this is the energy way of doing it. We say that the work is equal to the change in kinetic energy. We're saying that the force is negative and the displacement is positive, so we had to put this negative sign in here. The force is the friction force, which is equal to the coefficient of friction times the normal force. The normal force is the mass times the acceleration due to gravity. So when we solve for delta x, we get this part divided by f. Substitute in for f. Cancel the m's out, which I guess I could have done before I plugged anything in. And we plug it in, we get the same answer. And that happens a lot. There are cases where, in this case, it's a little easier using energy, but it's not super a lot easier. But it's gives us the same answer. Now, let me just stop here for a second. Okay, so those are the correct answers. And the key thing is when you do energy, when you use conservation of energy, you cannot find anything out about time. There's no time involved. You go from initial to final. We don't really care how long it takes to get there. We just look at work and change in energy. Here in the kinematics part and using the second law, we could actually calculate time. So if time's not important, a lot of times this is the easier way to go. If time is important, then we have to do this. Or we could use energy to calculate this and then go calculate that. So that's it for that one. Now we're doing problem 18, which is similar to what we just did on problem 13. We probably could solve it both using Newton's second law and kinematics or using energy. Anyway, so we have a pond. We have a sled of some kind here. And again, we're given the mass. So the mass of the sled is 10 kilograms. It's given a kick that imparts an initial velocity v0 of 2 meters per second. So we're going to move in this direction. We'll call x positive here. The coefficient of friction, kinetic friction between the sled and the ice is 0.1, so mu is 0.1. Use work energy theorem to find the distance the sled moves before coming to rest. Actually, it looks exactly like the problem we just worked. So it says coming to rest, so V is equal to V or V final, 0 meters per second. We know the weight is equal to the mass times acceleration due to gravity. So when this thing is moving, we have a force that's pushing backwards right here, which is the friction force. And the friction force is going to be equal to negative, and it's going to be equal to mu times the normal force. In this case, the only force that's pushing down is the weight, so the normal force is equal to the weight. If you did the sum of the forces in the y direction, you find that out, so we get negative mu m times G, which is the weight. Okay. Work energy says that work is equal to the change in kinetic energy, whereas the work is equal to the force times the distance. We have this cosine of theta thing, which, we can do that, but really I think it's easier just to think about what's happening. If the force is pushing it opposite the direction that you have movement, then you have negative work. Okay, we get the change in kinetic energy, which we're not going to use final versus initial. We're just going to use v squared minus v0 squared, which is the same thing. So if we solve for delta x, we get 1/2 m v squared minus v0 squared, all divided by f. And what I'm going to do this time is I'm going to just substitute, and I'm going to cancel stuff out. So we get 1/2 m v squared minus v0 squared, all divided by negative mu m g. The m's cancel out. So the final, and then this is 0. The negatives cancel out at that point. We can only do that once that goes to 0. Then we have negative in both terms. So we end up with v0 squared over 2g. So that's what delta L1 times mu. I forgot the mu part. So 2 mu g. Okay, now we can plug in the numbers. So v0 was 2 meters per second. Square the whole thing. So units are going to be meters squared per second squared. 2 times mu, which is 0.1 in this case, smaller than before. And g is 9.8 meters per second squared. And see, we have meters squared per second squared divided by meters per second squared, so that just leaves meters, which is what we want. So that's good. So 4 divided by 2 divided by 0.1 divided by 9.8, and I get 2.04 meters, which actually is not that far. So let me just let's just check. Okay, I've checked it, and that is the correct answer. So probably the coefficient of friction on ice, but it depends on the temperature and all the conditions and everything. So I can't really make any judgments about the coefficient of friction. So problem number 20 is in the spring potential energy section, and if we look at the potential energy due to a spring, it's just 1/2 k, which is the spring constant, times delta x, quantity squared. So it has a similar form to kinetic energy. Actually, that's potential energy, not kinetic energy. So spring potential energy is like that, which kind of compares with kinetic energy, which is 1/2 mv squared. So there's some similarity. So what we're going to do is we're going to draw a figure, of course. So here's our spring, and it's hung from the spring. And a light spring just means that it doesn't have any mass to it, so we ignore the mass of the spring. So we know that the mass of this thing is 2.5 kilograms. On a certain light stream, this is described by Hooke's law. Hooke's law says that the force is equal to kx, and it also means that the potential energy can be represented by this equation. So it tells those two things. And during the stretches, delta, we'll call this actually delta y, is going to be equal to 2.76 centimeters. What is the force constant of the spring? Well, here's the equation. And when this thing stretches, the force pulling on the string is due entirely to the weight of the object. So the weight is just going to be mass times acceleration due to gravity. And then we're going to have the force pulling in this direction from the spring. So our force is just the weight. And we have delta x, so we can solve for the spring constant by just taking the force divided by x, or in this case delta y. Let's put delta y in there. And we got to be a little careful on the weight. Again, as the weight is the mass times acceleration due to gravity, so we're going to have 2.5 kilograms times the acceleration due to gravity, which is 9.8 meters per second squared, all divided by delta y, which is going to be 2.76 centimeters, but we've got to convert that to meters because we have all this stuff in meters, so we're going to multiply by 0.1 meters per centimeter, or we could divide it by 100, same thing. So turn the calculator on. 2.5 times 9.8 divided by 2.76 divided by 0.01, and we get 890. And the units of K are force per unit length, so it's going to be newtons per meter. And we could figure that out from up here, but we just can look at the original definition. We could write that as 8.9 times 10 to the second newtons per meter. So that's a spring constant. If the 2.5 kilogram object is removed, how far will the spring stretch if a 1.5 kilogram block is hung on it? So this relationship still applies, but you can solve for delta x in this case because they're asking how far. So we can say delta x is equal to F over K, or we get in this case delta y is the displacement, is force divided by K. The force is just the weight, the new weight associated with the new mass. So we have the mass times acceleration due to gravity over K. We have K now because we're using the same spring. So delta y is equal to the mass, which is 1.25 kilograms times 9.8 meters per second squared, divided by 8.9 times 10 to the second newtons per meter. And because we have everything in standard units, newtons, meters, seconds, squared, and kilograms, we know we're going to be okay, and it's going to come out to be meters. We could, if we rewrote newtons as kilogram meter per second squared, we could do it the long way, but we're just going to assume that we have everything correct because we're using, there's no kill with anything. Okay, so you take 1.25 times 9.8 divided by 8.9 e to the second power, and we get 0.0138 meters. Delta y is equal to let's round it off here, 1.4 centimeters by multiplying by 100. And how does it compare with our other one? Well, it's about half. It is exactly half, actually. Half of this is that. And that makes sense because we've reduced the mass by half, which reduces the weight by half, and because Hooke's law is a linear relationship, it's you just ratio things really because we have the same spring constant. So twice the force, twice the displacement. Okay, then the final one is how much work must be exerted, must an external agent do to stretch the same spring 8 centimeters from its unstretched position. So see how much work must be done by an external agent. So let's look at this. Here's our mass. Well, actually, there's no mass on it. It's just spring. And so you apply a force. This is the force. This is the displacement. delta y. And so the work in this case is going to be positive because the force, external force, is pushing down. This is going, so they're both in the same direction, so it's going to be positive. And if you remember, work is equal to force times delta y, or it's equal to the change in spring potential energy in this case. So we have 1/2 k, let's call it y final squared minus y initial squared. So that's the change in spring energy, and the change in spring energy ends up having to be equal to the work. So we're not going to use this form. We're going to use this to calculate the work. And so y final is equal to 8 centimeters. We got 3 significant figures there. So if we divide by 100, you get 0.0800 meters. And y initial is equal to 0 meters, exactly. So the work is 1/2 k, which is 8.9 times 10 to the second Newton per meter, times 8 times 0.0800 meters squared minus 0 meters squared. And the units are going to be Newton meters because the meter squared here cancels out with the meters there, so you'll have meters left over. Newton meter is a joule, and that's what we're going to put it into. So we'll do that in a second. Okay, so we have 8.9. Oops, I forgot the decimal point. 8.9 e to the second, 890, divided by 2 times 0.08 squared. And I get 2.85 Newton meters. Newton times meters. And a Newton meter is a joule, so we get 2.85 joules. Okay, so let's stop her here. Okay, so I've checked it, and that is the correct answer. So that's what we're using work energy, in this case the spring potential energy, to calculate the work. Our next problem is problem 38 in chapter 5. So this is still in the same section. And this is another case of where we could solve the problem using projectiles and Newton's second law, but what we're going to do is use energy again. So we have a projectile that leaves at a 60-degree angle. It has its vertical and horizontal components. And actually, in this case, I don't think we even need to know what that is. And then we get up to the top, and so we have the same horizontal component. Actually, we do need to know that. Okay, so that's the peak. And it says that the projectile has a velocity here, v, 40 meters per second. And the angle is 60 degrees, so we can find the other two if we need to. Use conservation energy to find the maximum height reached by the projectile during its flight. So what we're looking for is the height from the point it's shot up until the maximum here. So this is the height. This is h final, this would be h initial, which we'll say is 0 meters. And we'll say this is some meters, that's what we're trying to figure out. And there's no external forces acting on it except for gravity, but that comes into play in terms of potential energy. So we have the change in kinetic energy plus the change in potential energy equals 0. Yeah, actually we do need to break it up into two components because at this point the velocity is just v sub x, which we can calculate from here. So that v sub x is going to be equal to v times the cosine of 60 degrees. And the cosine of 60 degrees is a half, so v sub x is 20 meters per second. Okay, that's a half. Half of 40 is 20. At this point, we only have the horizontal velocity. So this is 20 meters per second. V sub y is 0. So what we can say is that V0, our initial velocity, let's use i's instead. Use i's and f's this time. So the initial velocity is 40 meters per second. Our final velocity is equal to 20 meters per second. And what else do we know? We know the mass, but it doesn't really matter because it cancels out. So let's write the change in kinetic energy is 1/2 the mass times v final squared minus v initial squared. And we add that to the potential energy change, which is mass times acceleration due to gravity times h final minus h initial. And that equals 0. The initial height is 0. The masses cancel out. And so we can find the final height. We can solve for it. It's just going to be equal to v final squared minus v initial squared. Actually, this is going to be negative, because when we solve for this, go to the other side, they're going to change sign. So it's going to be v initial squared minus v final squared divided by 2g. So we'll divide by g to get h by itself. And so we have 40 meters per second, 20 squared minus 20 meters per second squared divided by 2 times 9.8 meters per second squared. And the units are going to end up being meters because the second squares cancel out and only one of the meters cancels out. So we have 40 squared minus 20 squared, that's 1200 divided by 2 divided by 9.8. And that ends up being 61.2 meters. So let's stop and handbook says 61 meters. And I guess we were only given the speed in 2 significant figures. And actually we really couldn't tell whether it was 1 or 2 because it was 40 instead of 40 point something. So anyway, we probably shouldn't have as many significant figures as I did there. So let's just take one of them off. So I have 61 meters is the maximum. And we could do that using kinematics, because we have the acceleration due to gravity, we have 2 of the velocity, so we could calculate delta y, and you still get 61 meters. Now, kinematics would allow us to how long it takes to get to that height, whereas conservation of energy just tells us how high it gets. So working problem number 45, and we have a driveway. So let's draw it like this, and the car starts at the top. Okay, this is the mass, so let's just write mass is equal to 2.1 times 10 to the third, 2.1 times 10 to the third kilograms. And that's the same as 2,100. And the reason we wrote it in scientific notation is so that we could show there were 2 significant figures. So we'll try to be consistent with the 2 significant figures. It starts from rest, so we know that we'll say VI, the initial velocity, is 0 meters per second. The driveway is 5 meters long. Okay, so it's at an angle of 20 degrees. And the distance, the length of it, not the height of it, is, so we're talking about that straight line distance, is 20 degrees. I mean, that's 20 degrees. That's the angle. The length is 5 meters. Not a very long driveway. Okay, again, two significant figures. The average friction force, so we'll call that F sub F, is 4.0 times 10 to the third newtons, which is 4,000 newtons. Okay, we'll just remember to work this to two significant figures. The question is, find the speed of the car at the bottom of the driveway. And we're using, you can solve this using Newton's second law, but it doesn't ask anything about time, so sometimes I want to answer the question without involving time. Just go straight to energy. And so what we have is that the work is equal to the change in kinetic energy plus change in potential energy. Now, we're going to have this friction force. Let's define a positive x to go this direction. So that's x. So our friction force is going to be going the opposite direction. So it's going to be pushing here to slow it down. So that's the friction force. And so when we calculate the work is equal to force times distance, but because the displacement is positive this way and the force is going the opposite way, we're going to have a negative sign. So we're going to have negative, and the work is equal to the force, the friction force, times the distance, delta x. And then we have the kinetic energy change, which is 1/2 mass times v final squared minus v initial squared. And then we're going to have the change of potential energy, which is the mass times the acceleration due to gravity times h final minus h initial. In this case, the height is going to decrease because we're getting to a lower level, and we always have positive in this term. In terms of height, positive is up, negative is down. And what that's going to be is h final minus h initial is going to be equal to negative. And then you take the length, called the length of the driveway L, and it's going to be the opposite side of this right triangle. So we have a right triangle that's made like this. This is the angle. So opposite side is the sine. So we take it multiplied by the sine of theta, where theta is equal to 20 degrees. And so if the angle is 0, then there's no height. If the angle is 90 degrees, the length would be the height. Okay, so those all check out just from an order of magnitude standpoint. So I think we have everything we need. We just need to solve for the final velocity. So before we do that, though, there are a few things that we can get rid of VI, because that's 0 meters per second. So let's get rid of that. Just 0. And if we rearrange things, what we're going to do is we're going to have 1/2 mv final squared. We have negative friction force times delta x. And then we have a negative sign here because when we move it to the left-hand side, it becomes negative. So we have negative mg. And let me just make a little more room in here. Times h final minus h initial. Okay, we want to solve for v final. So if we do that, we'd have v final squared is equal to, multiply both sides by 2 and divide by m. So we'll have negative friction force times delta x minus the mass times acceleration due to gravity, h final minus h initial. The 2 comes out front, and the mass goes to the denominator. So let's calculate it squared, and then we'll just square that into the square root function. So we have negative 2. The friction force is 4,000 newtons. Delta x is 5 meters. That's the distance along the plane. minus m, which is 2,100 kilograms. Move this over a little bit. I have a space. Okay. Times g, which is positive 9.8 meters per second squared, times h final minus h initial, and I'm still running out of space here. Squeeze it even further. Okay, so we have a negative sign. So let me go ahead and just make this positive. And then we have L, which is 5 meters again, times the sine 20 degrees. And the whole thing is divided by the mass, which is 2,100 kilograms. So what we basically have is this is going to increase the kinetic energy. The friction is going to reduce the kinetic energy. If we had no friction, if this went to 0, we'd get the maximum kinetic energy. And the kinetic energy would just be equal to, the masses would cancel out and would be equal to G times L, times the sine of the angle. If the angle was 90 degrees, this would go to 1, these would cancel out, and you would just have this times that, which would be that's acceleration times distance. I think that if you look at kinematics, it'd be much better. Okay, so let's plug the numbers in here. And I'm not going to do them all at one time. So I got negative 2 times 4,000 times 5. So this is the amount of work done in slowing it down by friction. So we have negative 40,000 Newton meters, which is a joule, plus 2,100 times 9.8 times 5 times the sine 20 degrees. And I get 35,200 joules. What's bothering me here is this is a negative number, and I can't have a negative number. So let me pause here and find out what I've done wrong. Okay, that didn't take too long. So this whole thing is multiplied by 2. That's the problem. So let's go fix that. So we'll have 2 times negative that, and then we have another right parenthesis. Okay, now what that's going to do is that's going to go to negative 20,000 times 2. Close it. Now it'll be positive. So 35,200 minus 20,000, 35,200 minus 20,000 is 15,200 times 2 divided by 2,100. And the answer is 14.5. And what we end up with is joules, which are Newton meters per kilogram. And remember, this is V final squared, so we still got to take the square root. Let's look at the units and make sure we're doing this correctly. We should end up with meters squared per second squared. So a Newton is a kilogram meter per second squared. That's from Newton's second law. Force is equal to mass times acceleration. And we multiply by meters and we divide by kilograms. So we divide the kilograms out. We have meters squared per second squared. So when we take the square root, we'll get meters per second. So now we take the square root of that. 14.5 meters squared per second squared. And I get 3.8 meters per second, which sounds familiar. So let me just check the solution here. Yep. Okay, so that's how you do it using energy. Now, if you're interested here, let's just do it using, so I'm going to insert a page here. We're going to show you how you do it using Newton's second law. And what we do is we calculate the acceleration. So if we sum the forces in the x direction, then we'd have the mass times acceleration. And what we have in the x direction is you're going to have, you can convert this weight into two components. You can do one that's along the road, which would be, and that's going to be in the positive x direction, so you're going to have W times the sine of theta. So that's this, and then in the opposite direction, you're going to have minus 4,000 newtons. Let's just use it at F sub S right now. We'll plug it back in later. Okay, so that's F sub F. And we know the mass, so that's going to be, the weight's going to be mass times G times the sine of theta minus the friction force. So we can solve for the acceleration, A sub x, and that's going to be mg sine of theta minus the friction force divided by the mass. So let's plug it in there. The mass is 2,100 kilograms times g, which is 9.8 meters per second squared, times the sine of 20 degrees, minus 4,000, which is your friction force, divided by your mass, which is 2,100 kilograms. And the acceleration should be negative, and it should be, let me make sure I'm doing this right. That should be positive, but it's going to be less than 9.8 meters per second squared, because if it's vertical, it would be 9.8 meters per second without any friction. Okay, so let's do 2,100 times 9.8 times the sine of 20. Make sure I'm in the right mode here. Yep. Okay, 9.8 minus 4,000. That's 3,040 divided by 2,100. That's an acceleration of 1.45 meters per second squared. So it's accelerating down the hill. If we had no friction, if this was 0, we'd have 2,100. Actually, all we'd have is 9.8 times the sine of 20 degrees. 9.8 times the sine of 20. We'd have 3.35. So if there was no friction, the acceleration would be 3.35. But because of the friction, it's slowed down. Okay, so that's the one we want to use. Now we use kinematic equations, and we're trying to figure out the velocity. So what do we know? We know delta x is 5 meters. We know that v0 is 0 meters per second. And we know the acceleration in the x direction is 1.45 meters per second squared. So knowing these three things, we have equation number 4, which is v squared is equal to v0 squared plus 2a delta x. And so we actually already solved for this. This part is 0 because we have an initial value of 0, so we have 2 times acceleration, which is 1.45 meters per second squared, times delta x, which is 5 meters. So we get 2 times 1.45 times 5 is 14.5, which should sound familiar. It's meters squared per second squared. Take the square root. It's going to be plus or minus, but we know it's going to be plus because just from the physics. So we take 14.5 to the 0.5 power, and we get 3.8 meters per second. So we get the same answer. And in this case, I don't know which one's easier. I guess it's not a huge amount of difference, but anyway, that's how it works. Okay. Off.